Hello and welcome to video 49. I apologize for any birds chirping or any other nature sounds you may hear. This is the current temperature. That hasn't happened here in Rochester, New York in 161 days, which represents 44.1% of the year. So my apologies. What we're going to talk about today is electric fields and how you calculate the electric field from these two test charges at this location, or these two charges at this test charge at this location over here. Before we do that, I just want to take one moment and talk about what an electric field actually is. This is just sort of my explanation of it, not necessarily how everybody would describe it, but I like to think about an electric field as a way that you could figure out what the force was from some distribution of charges on a test charge, something you're going to place there, without having to know the actual magnitude of that charge ahead of time. So it would be sort of like, I know when I go to the moon that I'm going to weigh less than I do on the Earth, and that's true for everybody. So that something is called a gravitational field. G on Earth, at least at the surface, is 9.8 newtons per kilogram, and that's the same for everybody on the Earth. On the moon, it's the same for everybody, it's just smaller. So there's something like that for electric forces, and it's called the electric field. Now what we're going to be talking about before we get into the actual problem is how to solve one of these. And I'm jumping right to one that has components. So when they're on a single line, when it's one-dimensional, the concept is the same, but it's definitely a little bit easier. So first what we're going to be doing is we're going to be sketching electric field vectors from each charge to the test charge, sort of showing qualitatively the direction and maybe the magnitude. Then we're going to have to figure out the direction of each of those vectors. We're going to have to figure out the distance from the charges to the test charge. We're going to calculate the magnetic field, or I should say, this really should be electric field. That's a typo. Let me go ahead, pause, and change that. I lied. That was magnitude. But we're going to calculate the magnitude of each electric field contribution. When we do that, you got to be careful about prefixes: nano, milli, micro. When you deal with charges, 1 coulomb is actually a lot of charge. So most of the charges you deal with in real life are going to be nanocoulombs, microcoulombs. With distances, you also have to be careful when you do that. Once you have the actual electric field magnitudes, you're going to use this information from before, and you're going to get the x and y components of the electric field. You then treat this basically like a vector problem. You add the x components and the y components separately. Then once you have those, you get the magnitude and the direction of the overall resultant, or in this case, the electric field at a particular location. So just looking at this, you can see that here's the test charge, and we can ignore the number here, because even if this test charge was not here, the electric field still would be. So if we were to draw a vector, you want to think of this as being a positive test charge. From the -2 charge, that's going to go up and to the right, like so. And it's probably going to be fairly large because that charge is close to the test charge. Now, this 3 is going to be pushing this positive test charge away. Away, in this case, is going to be down and to the right. So we've now sketched the electric field vectors. Let me label these. It's helpful to give them something of a name. So we'll call this A and B. It's not that creative, but they don't care. So this would be the electric field due to B at that location, and this would be the electric field due to A at that location. So now what we need to do is we need to get the direction, or the reference angle, if you will, of both of these vectors. So you can see that this one is going to be maybe 45 degrees-ish as drawn, and this one might be 45 degrees below the y-axis, something like that. But we've got to actually do the math. And to do that, let's actually zoom out a little bit. And I'm going to turn on some grid lines. And if you look at this, you can see there's a triangle going like so, or like so. So if you go here, this goes 1, 2, oops, 1, 2, 3 over, and 1, 2, 3, 4 down. 3 over, 4 down. And the hypotenuse of that triangle is going to look like so. 3, 4, and I may have chosen this to make the math easy. Some of you know this is 5. So if I'm going to get this reference angle, let's call this a reference angle. That reference angle is going to be the inverse tangent of the opposite over the adjacent. So that reference angle is going to be equal to the inverse tangent of 4 divided by 3. And when you do that, that's going to give you a reference angle that is, I did the math ahead of time, 53.1 degrees. Or if you want to think about this as the overall direction, it would be 360 minus that, so it would be 356.9 degree direction overall. I leave it to you to think about it in terms of reference angles or overall direction, but you got to be really careful about whether x and y components are positive or negative, as you'll see in a few minutes. Now going back to the other charge, you can see that this makes a triangle. So if this was A, B's triangle is going to look a little different. Test charge is over here, and it's going to go up to and over 1. So up to, over 1. It's going to be a lot smaller triangle to try to draw, but that's okay. Like so. And this side is 1, 2, and this side is going to be square root of 3. Again, what we want to do is we want to get the reference angle. So over here, this would be the reference angle. And that's going to be given by the inverse tangent of the opposite over the adjacent. By the way, I got that using Pythagorean theorem, and it's a special triangle. But the inverse tangent of 2 divided by 3, and that's going to give you an angle of 63.4 degrees. And an overall direction that is also 63.4 degrees. So now that we have the directions and we've got the magnitudes of the distance, which was step number 3, we can go ahead and we can start to calculate the actual electric fields that are involved. And to make that a little easier to see, I'm going to turn off the ruled lines. So in general, if you want to get the electric field due to a point charge, it's kq over r squared. We're going to be using a k of 9, well, I mean the universe decides the k, but we're going to round to 9 times 10 to the 9th newtons per coulomb. So for A, we're going to put in 9 times 10 to the 9th newtons per coulomb times the q, which now here's where we got to be really careful about the prefixes. Now if you look at the statement of the problem, it says that all charges are in nanocoulombs and all positions are in millimeters, which means their distances are also in millimeters. So when we have a distance, in this case of 5, that's going to be 5 millimeters, or 5 times 10 to the negative 3 meters. Don't forget to square it. And that's going to be a charge of 3. It's nanocoulombs, so it's going to be 3 times 10 to the 9th coulombs. That's probably a place where many students make a mistake. So if your answer you get looks exactly the same as mine, but the power of 10 is off, chances are you didn't take the prefixes into account. So when you plug that in, I got 1.08 times 10 to the 6 newtons per coulomb. So we now have the magnitude of the electric field due to A, and we have the direction. Both very helpful. Now for B, it's going to look pretty much the same, except that the numbers are going to be different. K has not changed and will not change. That's what constants do or don't do. The charge is now -2. The minus just means that it's attractive. So that's -2 times 10, again, to the minus, oops, this was supposed to be -9. Did everybody catch that? That was -9 because it was nanocoulombs. Coulombs over a distance that is square root of 3 times 10 to the -3 meters squared. And when you do that, you should get a B that is 6 times 10 to the 6 newtons per coulomb. Notice it's actually stronger than the magnetic or the electric field from A, which makes sense because even though it's less charge, it's much closer than is A. So we're a lot of the way here. At this point, it's basically a vector problem. So what we're going to want to do is we're going to want to create a table. So we're going to want to get the x components and the y components. So let me be fancy. Make a table. Like this. So we're going to want to get the x component. We're going to want to get the y component. And we have the electric field due to A and the electric field due to B. Before I start plugging numbers in, let's look at this. The electric field due to A is going to have a positive x component and a positive y component. And the electric field due to A is going to have a positive x component but a negative y component. In other words, the only one that's going to be negative is the y from A. So let's go ahead and put that in. I'll even put it in a different color. So the y from A is going to be negative. All the others are going to be positive. So when I plug that in, that's going to be 1.08 is the mag times 10 to the 6th. Well, let me make sure I'm giving you guys the right numbers. I am. Newtons per coulomb. Times, we've got to take the cosine, and we can do the cosine of the reference angle, 53.1 degrees. And when I did that, I came up with 0.648 times 10 to the 6th newtons per coulomb. For the y component, it's going to be the same magnitude, the 1.08 number. Except it's going to be times the sine of 53.1 degrees. And when I do that, I got negative 0.869 times 10 to the 6th newtons per coulomb. Then for B, when we plug that in, we're going to get 6 times 10 to the 6th newtons per coulomb times the cosine of the different reference angle, 63.4 degrees. And that gives us 2.687. Again, times 10. Well, we stick with the black. .687 times 10 to the 6th newtons per coulomb. And then for the y component for B, it's going to be 6 times 10 to the 6th newtons per coulomb times the sine of 63.4 degrees. And when I put that into my calculator, I'll write it in black again. I get 5.365 times 10 to the 6th newtons per coulomb. Then what we want to do is we want to add these numbers down, just like we do with vector problems earlier in the year. And when I do that, I get 3.35 or 335 times 10 to the 6th. And for the y component, I get plus 4.496 times 10 to the 6 newtons per coulomb. Then again, like any other vector problem, I like to sketch what it's going to look like. So this side is going to be 3.335, don't forget, times 10 to the 6th. The y is going to be 4.496. The resultant, the net electric field vector, is going to be diagonal like this. And to get the theta, we are going to take the inverse tangent of the y, 4.496, divided by the x, 3.335. That's going to give us a theta that is 53.4 degrees, which, because it's in the first quadrant, is the same as the overall direction. And that's going to give us a magnitude for the electric field using Pythagorean theorem, this squared plus this squared, take the square root, of 5.60. Again, don't forget the times 10 to the 6 newtons per coulomb, again, in the 53.4 degree direction. And we have now calculated the electric field at that point. Now some of you may be saying, why do we put so much time into calculating this? I'm only going to do it once. Well, hopefully you only have to do it once. But if we want to know the force acting on a particular charge, that makes our life significantly easier. Let me show you what I mean. Let's just say I was to tell you that I was going to place a 6 nanocoulomb charge. So we're going to place a 6 nanocoulomb charge right there at that location. So we plop it in and we put it right here where the test charge is. To get that force, we can just go right to the definition of the electric field, which is force per charge. Or practically speaking, if we want to calculate a force, it's always the charge times the electric field. Notice electric field is a vector, it has direction. That direction is exactly the same as the direction of the force. The charge just tells you what the force actually would be now that we know the charge. Electric field tells us what it would be without having to know it ahead of time. So I just literally plug in 6 nanocoulombs, 6 times 10 to the negative 6, or negative 9 rather, coulombs, times the electric field, 5.60 times 10 to the 6 newtons per coulomb. And when I plug that in, that is going to give me a force that is 0.0336 newtons, which is also known as 33.6 millinewtons, as long as we're practicing using our prefix. And a direction is going to be the same as the direction of the electric field. The reason it's going to be the same is because it's a positive charge. The electric field tells us the direction of the force a positive charge would feel. Now just to switch things up, if I was to give you a charge on the other hand that was negative, let's just say the charge that I gave you was negative 4 nanocoulombs. We don't have to redo the whole problem. We just do F equals QE again. And now the Q you plug in is negative 4 times 10 to the negative 6, or 9 rather, coulombs. The electric field stays exactly the same. And you're going to get an answer that is negative. What the negative means is that it is going to be attractive, and it's going to be the opposite direction that it was before. So I can just tell you 4 is 2/3 of 6. So the magnitude here is going to be 22.4 millinewtons, or 22.4 times 10 to the negative 3 newtons. But the direction is going to be the exact opposite of 53.4 degrees. So that's going to be this plus 180 degrees. So some people like to call that 53.4 degrees below the negative x-axis. I like to go with the overall direction in terms of 360. So let's just add 180. And when you do that, you get a direction that is 223.4. Is that 30? No, I'm sorry. Hold on, let me make sure I added that right. Oops, I mean 33.4. So what did we do? What have we accomplished here? If you look at this kind of problem, now I gave you one with only 2 charges. You could do it in principle with an infinite number of charges. But we have charges that each would push this in an x direction and a y direction. And we calculated the electric field. That is, what would the force be on a 1 coulomb positive charge if it were placed there? We determined the distance between each charge and the test charge location. We determined the direction using a little trig. We then calculated the electric field for each charge separately. We got the x and y components of each electric field contribution. We added those components separately and used those components to get the direction and the magnitude of the total electric field. Once we had that, we then showed for 2 different charges that we placed there, one a positive test charge of 6 nanocoulombs, one a negative test charge of -4 nanocoulombs, what the magnitude and the direction of the force would be. As always, I hope that you find this useful. I hope it's not too overwhelming, and see you next time.